Welcome to this explainer from the Foundry by Forge College. I'm your host, and today we're basically putting on our hard hats because I'll be stepping into the role of your enthusiastic architectural building inspector. Look, we've laid the foundation, we've poured the concrete, and now we're going to earthquake-proof those blockchain blueprints. We'll be evaluating risks and system trade-offs to make absolutely sure your architecture can withstand whatever the real world throws it at it. Okay, let's dive right into this. Here's our inspection agenda for today. First up, a blueprint refresher. Second, the 3 buckets of risk. Third, navigating system trade-offs. Fourth, mental models for safety. Fifth, building your risk register. And finally, runbooks and tabletop drills.
All right, part 1, the blueprint refresher, preparing your architectural blueprint. Before we start looking for cracks, we really need to examine the overall structure. Let's look at the progression of your architectural blueprint so far. You started off with ledger mechanics back in Lesson 1, you layered on your use case priorities in Lesson 2, and then you combined them into a full architecture in Lesson 3. All of those artifacts, the transaction life cycles, the priority lists, the wallet flows, they all converge right now for this final, ultimate risk assessment stress test. Moving on to Part 2, 3 buckets of risk, categorizing the chaos.
Look, you simply can't fix everything all at once. It's impossible. Before we can even begin to fix a problem, we have to organize our anxieties into manageable categories just to understand the threat. Usually, a system failure falls neatly into one of these 3 labeled disasters: operational risks, technical risks, or business risks.
Let's start with operational risk. This one is really all about people, processes, and tooling failures. It's the human element. Think about things like misconfigured monitoring or node provisioning errors during a rapid scale-up. It's kind of like accidentally creating a split-brain scenario on your network just because someone had a little too much coffee and types the absolute wrong configuration parameter into the command line. Hey, it happens, but we've got a plan for it.
So the crucial point here is understanding the difference between these next 2 buckets. Technical risk involves the actual nuts and bolts, distributed systems issues. We're talking consensus stalls, state replication bugs, or an external oracle completely failing on you. Business risk, on the other hand, zooms way out. It's about regulatory exposure, failing to meet contractual obligations, or broken economic incentives. You really need both that micro and macro lens to truly protect your system.
All right, Part 3, navigating system trade-offs, the art of compromise.
I totally know your instinct as an architect is to try and achieve 100% perfection across all your metrics, but mathematically speaking, in distributed systems, something's got to give. It's a fundamental art of compromise. Mapping a theoretical trade-off to a concrete architectural symptom, and then providing an actionable mitigation pattern, well, that matrix is your best friend. It's exactly how you translate abstract theory into practical boots-on-the-ground engineering decisions.
Let's look at a classic tension: consistency versus availability. Do you want your data to be perfectly, synchronously correct across all nodes right this very second? If you do, you're going to have to accept higher latency. Or do you just want the system to stay online, be highly available with asynchronous replication, and figure out the exact state a few milliseconds later? You literally cannot have both perfectly at the exact same time.
Then there's safety versus liveness. Now, I know a consensus stall sounds like a sci-fi horror movie where the spaceship's engines mysteriously die in deep space, but actually, it's just a protocol prioritizing safety over liveness during a network partition. The system intentionally halts to avoid an inconsistent state. Prioritizing liveness, however, means the network just keeps moving and trusts that it can resolve any conflicting commits later on.
Part 4, mental models for safety, frameworks for fast decisions.
Now, what's really interesting here is how we navigate these choices without pulling our hair out. We use mental models. Think about the separation between the control plane and the data plane. Your control plane involves high-risk, low-frequency events. We're talking governance changes, node joins, or parameter updates. That is where you allocate your heavy automation and your most intense testing. Your data plane, though, handles high-volume, lower-risk everyday transactions, and that is exactly where you want to optimize for pure speed and a great user experience.
Another favorite shortcut of mine is the safety fence model. Imagine drawing concentric virtual fences around your absolute most valuable assets. Think of a high-security vault. Your hardware-backed private keys, guarded in the deepest, innermost center fence with the strictest possible controls. Meanwhile, your basic read caches live out on the cheaper outer perimeter, where a breach isn't a catastrophic, system-ending event.
Moving right along to Part 5, Building Your Risk Register, Documenting the Defenses. Let's move on and see how this builds. As you've probably seen in the other courses and programs you're taking with us at Forge College, rigorous documentation is exactly what separates a theoretical idea from a viable, production-ready product. And it builds into this really satisfying 5-step workflow for formalizing your mitigation strategies. Step 1, identify the threat. Step 2, quantify its likelihood and impact. Step 3, prioritize it. Step 4, mitigate. And Step 5, verify.
When you quantify, you absolutely want to avoid what we call subjective drift. We use a strict 1 to 5 scale, firmly anchored to concrete reality. So a score of 1 is just a minor cosmetic effect, but a score of 5? That's not just a bad hair day. That's a material ledger inconsistency or a total regulatory breach. Anchoring these numbers ensures you spend your engineering budget putting out actual house fires, not just dealing with burnt toast.
Finally, Part 6. Runbooks and tabletop drills, preparing for impact.
Look, this is where the rubber actually meets the road. This is where we prove our meticulously drawn blueprints hold up when the fire alarms go off in the real world. It all starts with SLOs, service level objectives. These are your explicitly measurable expectations for system behavior. For example, demanding that median commit latency stays under 300 milliseconds for critical paths. If you chose a synchronous commit earlier that spikes your latency, well, you've got to justify it right here against the specific priorities you set back in Lesson 2.
To measure those SLOs, absolutely every single component in your architecture needs these 3 essential monitoring primitives attached to it. First, a health check, simply to tell you if the process is actually up. Second, a business metric, like transactions per minute, to show if it's doing useful work. And third, an integrity check, like ledger hash alignment, to mathematically prove the data is completely correct.
Once your monitors are in place, you need to run tabletop drills for some very specific sweat-inducing nightmares, a validator compromise, a total Oracle outage, a large-scale network partition. You have to actively rehearse these scenarios to ensure your instant containment and failover sequences are completely battle-ready long before a real crisis hits.
Which leaves us with one final, provocative question to ask yourself after every single drill. What observable condition marks the closure of the incident? You need to know exactly what recovery looks like and when it is officially 100% complete. And that wraps up our explainer and architectural inspection for today. I highly encourage you to visit forge.college to learn more about this subject and explore other fascinating Web3 topics. Thanks for learning with me, and happy building!